My name is Pinelo. I'm the head of data science, cloud infrastructure, and development at the Air Center. Maybe we could turn off these lights here, or. Is this better? No, it's too dark now. Yeah. Okay, so, and I'm going to talk a little bit about compute in the reality of the Air Center, in our reality. And this will lead why this full support to Julia, why we like to support Julia, why we like to support communities, why we do that, and why Julia specifically. And specifically for Earth observation, which is most of our work. So when we talk about computation, we often talk as if it was abstract, as if it existed outside geography, energy systems, outside politics, and outside consequences. But computation is not abstract. It's certainly not abstract for us. It's certainly not abstract in the contexts we operate. It is physical, it consumes energy, it occupies space, it depends on networks, and it inherits the constraints of that world in which it operates. Over the past years, through projects at the Air Center, through the Atlantic Cloud and other initiatives, through work with local communities, we have learned this the hard way. Not as a theoretical exercise, but as a field experiment. We had to build systems that have to work continuously, reliably, and under real limitations. So those limitations are not bugs. They really are the design space. We have to design within that context. So energy availability, latency, cost, jurisdiction, environmental impact, these are now first-order variables, and they're not afterthoughts anymore. So the question is no longer how to compute more, but how to design compute that makes sense in this real world. So today I want to reflect briefly on what we have learned so far, and then look forward and what it means to design computation deliberately, under constraints, and with intent. So, talking about 4 main points, constraints, what are what the constraints that we've been facing forced us to learn, what worked, what did not work, and what changes, what happens next. So it's not a success story that I'm going to tell. It's basically more like a field report than anything else. So the Air Center exists in the international context, and we are part of several international networks like the Marine Biodiversity Network, United Nations Environment Programme, the European Space Agency laboratories, and the European, the RCTS, so the European Network for Scientific Computing. And we also have partners across several continents, spanning all the Atlantic. So you might look at this and think, okay, this looks like there is this is a map of reach, right? You could see it that way. What we actually see after a while is that this is a map of latency, of regulation, of energy variability, that becomes super apparent when you try to work with these geographies. So it's not a map of reach, it's a map of constraints, real constraints. And these constraints basically disqualify centralized architectures that we tend to use or become accustomed to. So in the Atlantic, these constraints are impossible to ignore. I mean, the distance matters, connectivity matters, energy matters, all parts of the system matter. So weather matters. And yet this region, it's a peripheral region, and it's treated as so in the global compute architectures, something to connect to rather than something to design from. And based on our reality, we have to adjust this. We have to design for this reality. We have to deliver to this reality. And the Air Center was created in this context. I mean, it's not as a data or a data center project, but and not as an academic initiative, but as a platform for collaboration. And if it's for collaboration, it has to be reliable, it has to work, and it has to work in these different contexts. So collaboration across geography, across disciplines, across institutions, and many of these face similar constraints. So working from the Azores and across the wider Atlantic, from Europe to Africa, from the Americas to island states, we have to design systems to assume latency, that assume limited resources and that assume long-term operations rather than short-term demonstrations. This is our goal, from short-term demonstrations or prototypes to long-term operational systems. So this is where many of our systems emerged from. It's from this context, from these limitations. The Atlantic Cloud is an example, which is still in its infancy, but it's an initiative that we care very deeply about. The Atlantic IoT Network that started as an IoT network for the city of Angra, the city where we are now. It became the IoT network for the island, then became the Azores, and now it seems to be expanding through the Atlantic. And a range of other operational services supporting science, communities, and industry. And not as experiments, but infrastructure that has to function under real conditions, under the limitations, the constraints we face. So that Atlantic perspective is not a limitation. It's a forcing function. It makes these trade-offs visible. And these trade-offs, by the way, are increasingly global. So they offer a preview of the constraints that we face in the globally, worldwide, that the world now is beginning to face, like energy limitations. So we always work at the Air Center aligned with communities and aligned with sustainable development goals. So we want to support local communities, local economies, and for that, we make sure we are aligned with the Sustainable Development Goals. So now I'm going to go quickly through a few examples of lessons we learned through projects we've done or initiatives we maintain. So supporting a municipality to install photovoltaic panels, they needed to know where there's more sun. Basically, it's a fair enough question, and there's data for that. Copernicus Atmosphere Monitoring Service has that. We went back 10 years, and we made a map for the municipality to make an informed decision. So the output here is that, like, we tend to focus a lot on our work, right? Our data sets and stuff, but the real world cares about the impact, cares about the information that comes out of that, right? So just a call here for this. So local energy production mattered much more than the time series that we use to do that. That's just the data. What the real world wants is always, of course, information. This is support livestock producers, an alert system that's been operational now for maybe 4 years or so. And the lesson here is mostly that prediction accuracy was secondary to trust, to uptime, and to explainability. And the explainability is super important for this specific. It was very important for this specific project because we started the project based on the existing scientific knowledge, and we came to challenge that, and we made progress there too. The project helped science to make some progress as well. In another one where support farmers take care of the health of vineyards, seasonal reliability mattered more than model sophistication. what again matters is that we can deliver information. So a harder lesson was when we moved on to a project where we actually developed hardware, and we come to realize that we did solve the technical problem, but we didn't solve the adoption problem. So for that delivery, you probably need another round of funding to be able to have the system that works, bring it to fruition. Right? So in hardware and operational systems, funding the build is not enough. We need to look way beyond that. The tricky part, of course, is how do you get enough funding to also get things out there before proving that they work. But it's not a technology of failure, it's a failure of how we fund hardware-based compute. So another project or initiative we have, Adriano is going to talk more about this later, it's supporting scientists and the industry. Global monitoring of internal waves in near real time, and this is a global initiative. We're monitoring across the globe in near real time. Oh, and here again, I mean, continuous operation was the lesson. That matters more than peak accuracy of the model. So in the age of AI, because AI seems to have taken over compute seems to now be similar or synonymous to nearly to compute. All of this collapses if compute cannot be operated, like delivery to users. So the applications stop working if we can't compute. We cannot simulate. We cannot do data analysis. We cannot do AI. So we, in order to address the need for resilience, but to address the differences that we find across the Atlantic, we started the Atlantic Cloud, which is basically shared infrastructure. It's a series of nodes working together across the Atlantic, different compute nodes. So it's not about scale, of course, it's about placement. And we need to do this because hyperscalers could not give us predictable latency, they couldn't give us traditional clarity or operational sovereignty. And cost stability. So it's not about a centralized infrastructure at all, it's about a coordination layer, basically between us, Air Center, and all our partners across the Atlantic. So the Atlantic IoT network, as I mentioned, started here, but it seems to be growing, and it grows for it's low cost, it's low bandwidth, it's low power, so it takes less assumptions, it takes less for granted. So it's designed for environments where power and bandwidth are assumptions and not guarantees. So this brings us to compute efficiency, right? So compute efficiency, we have at least 3 layers. We have the software layer, the hardware layer, and then the system level efficiency. And we think that this is the problem. I mean, this is the bottleneck now. This is what we have to address. In terms of software efficiency, we are, of course, concerned, and we have to keep improving. In particular, not that software isn't great, it's just that in many instances we're using old software that could be more efficient if it was rewritten or some parallelized, etc. Hardware efficiency, it's a matter of power density now. Power density increased by tenfold in the last 10 years. But system level efficiency, so the useful compute divided by the cost of the operational cost of operations, the total cost of operations. So the efficiency gains come from architecture and placement. So the system, what we're calling here system, not just raw power. So in terms of computing efficiency in software, we tend to use highly performant languages, and of course that's why we support Julia so much. It's the 4th edition here of the JuliaEO. I mean, these matters, all of you make difference here. Like, all your work will have a huge impact when you stack up years and years of operations of your software. When it becomes operational, it's hard to ignore the power efficiency of GPUs. You could argue that a lot of computation should transit from CPU-based to be GPU-based, because the price per core, both of building and maintaining, operating, is way, way lower. And then green compute has been largely seen as a data center problem. But if you can't operate in data centers for the reasons we mentioned, then how do you solve that problem? So you have to think about it as a system problem, and we have to bring all the components to the fore. Data centers, by the way, they use up to 40% of their energy just for cooling, so not even the essential thing they have to do, which is to process and store data. They consume 2% of global electricity usage, and they consume more energy than overall data centers in the world, more energy than many countries. So what we have found at the Air Center is that energy is really, the availability of energy is a limitation. And the world is facing that now because of AI, because of the use of GPUs. We've been learning that in the last few years too. Singapore has 70 data centers for the Asia-Pacific area, and the demand on land and energy was so intense that had a moratorium to data centers in 2019. So they said, well, no more land, no more energy for data centers, that's enough. And this lack of energy is creating things that we might not all agree with. So Microsoft is reactivating nuclear power to power AI and AI data centers. Amazon, Google, and OpenAI are investing in nuclear power. And in the current, the amount of energy required for the data centers dedicated to AI that are currently being built is around 600 terawatts per year, which is double what Brazil consumes. The whole Brazil with 300 million inhabitants consumes every year. So another issue about compute, the traditional compute in data centers, the hyperscalers, is fresh water consumption. So they use a lot of water. In 2014 alone, the amount of water used in the data centers in the US alone was enough to cover the area of Germany and Poland together with 10 centimeters of water. And finally, one last example. I promise to move on. If we were to not have used energy for cooling, so not all countries report energy used by data centers, etc., but Germany did a really good report of this. They did report for a few years, consecutive years. If Germany had not used cooling for the data centers, if the data centers were more efficient, then they could have run 5 extra years without the same energy. And it turns out this might not be impossible. So AI power growth is directly tied to the moratorium in Singapore, nuclear reactivation, grid stress, not to mention prices and availability. So energy is no longer the cost, not just a line of cost on the budget, it's actually a hard limit. We hit a brick wall in that sense. So the Air Center is supporting or has a spin-off called At Depth, which aims to do sovereign underwater edge clouds. So high density, energy efficient, private AI compute deployed in ports. AI or HPC, in terms of setup, it's irrelevant, but zero energy for cooling, so 40% less energy or 40% more compute, any way you want to put it. So the vision is a world where cutting edge computing power and environmental sustainability coexist. We showed it's possible. We exist because of the current cloud model that does not resolve the constraints of field at the air center, and we believe the new private clouds will require. We're not an hyperscaler. We don't want to be the cheapest compute, and the goal is not general purpose public cloud. Power density has increased a lot, and we can have now in one machine more power than we can cool if we cool through the traditional methods. If we place the load underwater, we can cool this passively. So the problem is no longer powering racks, it's where the racks are allowed to exist, where you have availability of energy, feasibility of cooling, where you don't rely on water, so water scarcity, it doesn't matter, and urban deployment limits. So we design for density and locality and long-term operation. We proved that we can have passive cooling, no thermal throttling, not a lot of pressure on the hardware because there are no temperature spikes, so much more constant operations, and the cost is not higher. So we believe the future of compute is not abstract, it's local, it's constrained, and it is intentional. Languages like Julia or systems and architectures that respect this will matter, will be on the map, and the rest will not. So to conclude, I mean, over the past few years, we have learned that computation does not fail where benchmarks fail. It fails where systems meet reality, where we deploy in a different reality. For example, we cannot have a system that works in Paris deployed in the coast of Nigeria, for example. So energy is intermittent in many places. Latency is unavoidable. We have to think about funding deployment and operation, not just funding deployments. And we have to create an infrastructure that can be adopted, can be used. And so for us, at least, these are not edge cases. These are the conditions under which we operate. And most of the world is becoming to realize that some of these limitations actually are global, so like the lack of available energy. So what this means is that the future of compute will not be decided solely by faster chips or larger models. It will be decided by where computation is allowed to exist and how long it can operate, and crucially, how it can be trusted. Who trusts that infrastructure and those models? So the shift, that implies a shift in the problem or in the way to perceive the problem, from performance to placement. We believe placement is crucial, and regulation, NIS2-driven regulation, is a major factor of that. So it's not about squeezing more flops from silicon, it's about designing systems that respect physics, geography, energy, and institutions. Systems that can run continuously, not just prototypes. So languages like Julia are a crucial part of the puzzle, and that's why we support Julia. And as you're going to see next, we're trying to port some existing loads to Julia, and continue to organize this event.